So my talk is from zero to machine learning in 45 minutes. Give me a second while my clicker works. There we go. So can you guys see my screen? Fine?
Looks good.
All right, cool. So my name is Harnoor Minhas, and I'm a senior data engineer at Quicken Loans. A little bit about myself. I love technology. I love data. I love cloud technologies. And I'm also a little bit into machine learning. I'm no way an expert, but I know enough to be dangerous. I also like playing video games. I'm also a little bit into cryptocurrency. If you're interested, let's chat later. At one point, I had around 16 video card rig in my basement, heating up my basement and making me some money. All right, so what are we going to learn today? So we're going to learn what's artificial intelligence, what's machine learning, what are the three main types of machine learning, and then we'll get into some examples and hopefully some entertaining examples of how it's used in the industry. And then we'll go a little bit deeper into reinforcement machine learning, which is also one of my favorites. I think it's one of the most complex as well. Then we'll get into deep racer, which is, in my opinion, one of the fastest ways of getting into reinforcement machine learning. And we'll use some Python. If you don't know Python, that's fine. There are some predefined templates we can use. And then in the end, we'll see how a deep racer model works. So I might use the word ML and machine learning interchangeably, just means machine learning. So you might think that machine learning is only limited to a few companies, a few places. I mean, I used to think the same, but I was surprised to know machine learning is everywhere around us. If you use Google Voice, or if you use Siri, Alexa, they use machine learning. If you use Spotify, Spotify actually uses machine learning to identify which ads to show you based on your interest. If you use credit card, they use a credit real-time checks for fraud detection. Facebook, Instagram, they're trying to show you ads based on your interest and a higher likelihood of you buying something from them. Chances are you probably used a smart elevator sometimes. So, you know, it's all around us. So how does it work? So it's based on a simple thing called artificial intelligence. It's made up of two words, artificial and intelligence. Artificial means something that's not natural. Intelligence is the ability to acquire and apply knowledge and skills. So with AI, we try to emulate the ability of humans to learn based on some information, some data. So a simple example of AI would be a chess, a game, or a Tetris. It just does something on its own. It may not be learning. It's programmed specifically to do something specific. Think of a robot which knows how to walk on a hard surface. So what's machine learning? So take the same robot, for instance, now. You take the robot and try to make it walk on snow or grass or sandy surface. It's gonna suck, right? Because it's not programmed to do so. So that's where machine learning comes in. So think of the same robot now, and you add some sensors like a gyroscope, add some cameras to it, and now it has these moving parts, and it's getting feedback as it moves, and it's learning from the feedback. And as it goes, it starts learning how to walk on those surfaces. That's what's machine learning. All right, so talking of machine learning, here's a picture of a mouse eating a cake. So why is there a picture of a mouse eating a cake? Like I mentioned, I like playing video games. That's my gamer tag, mouse eating cake. My daughter came up with this name. But going back to the picture, did you have to struggle for a second to say that's a cake and that's a mouse and that's a mouse eating a cake? Not really, right? Because over time, we've trained our brain to identify things. So that brings me to how do we learn? So all these years, we trained our brain to identify these things, these actions, by looking at pictures, going to the zoo, looking at animals, interactions with people in daily life. So our brain learns over time and we don't even think about it. So let me show you this picture, for instance. So I know you can't really tell me, maybe send a message in chat, I'll check later. It'll be interesting. How many of you think this is a mouse? I'm pretty sure most of you think, or a rat, right? So let's say 99% confidence that this is a mouse. How about this one? How many of you think this is a mouse? And if you were saying this is a mouse, what's your confidence level? I would say probably like 15 to 20% confidence level that this is a mouse. But what if I tell you this is actually a mouse? This is the behind of a mouse. Now you actually take that information back and you learn from it. And next time I tell you that's a mouse, I mean, I ask you, is this a mouse? You know this is a mouse because you learned that. That's how kind of machine learning works. Uh, so that's all cool, machine learning, artificial intelligence. But why should we really care about machine learning? So machines never sleep, they work 24/7. They can do a lot of things which are beyond human capacity. Just imagine you can build machines which are first of all specialized. Then you can add more RAM, you can add more memory, you can add more processing power, and now you can almost build a supercomputer with superhuman capabilities, which can surpass the human capabilities, much like tens, thousands, 100,000 times. Also, machines don't complain about working hours or working on holidays. All right, so machine learning also helps us in our medical field. So machines have come really far at diagnosing a lot of diseases, a lot of things which are harder for humans to get good at. So let's take an example of a pathologist. So typically a pathologist scrolls through 1,000 photos every 30 minutes. Think for a second, that's almost half second per image. And they're trying to identify a tiny outlier on the image to say this is a tumor or this is an anomaly and they should be looked into further. So so I'm sure like there's a lot of missed scans and there's a lot of false positives. So now the machine learning models can actually recommend, hey, can you look at this one again? I think you missed this one. Or I think this was a false positive. So that can save you a lot of time and money. Also, think if somebody has a rare disease. So if the disease is rare, think for a second, how are the pathologists trained to identify these diseases? By actually showing them images and saying, hey, this is an image of somebody having a disease. Now, if the disease is so rare, how do you train people on that? That's a problem. But machines, on the other hand, can actually access their database of terabytes and terabytes, or maybe petabytes of data, and they can say, hey, I think this is probably the disease this person has. The machines can really help you there. They also help us with the quality of life. I'm sure a lot of you have smart devices, IoT devices. I particularly love my smart sprinkler system, which actually helps me save water and I don't have soggy grass when it rains. Uh, Other things like thermostats, saving you money, Roomba, if you're lazy like me. It also helps us with our entertainment. I'm sure most of you use Netflix. So with Netflix, and this is not my screen, by the way, guys. Like a lot of people ask me, hey, this is your homepage. No, this is not mine. This is just a screenshot from Google. So if you go to Netflix, you know, Netflix tells you, hey, you want to watch this? You want to watch this show? You watch this show, maybe you like this show. So it's based off of machine learning. And if you watch the show, you give some feedback to Netflix saying, okay, I really like this. If you don't watch it, it knows you don't really like it. If you watch a whole series over the weekend, it knows you really like it. So I'm sure a lot of you know that, but did you know that every time you go into Netflix, it actually shows you different thumbnails for the same shows or movies? So what it's trying to do is increase the likelihood of you actually clicking on the show and watching it. So talking of movies, let's talk about black and white movies, for instance. Machine learning has come so far that it's actually 97% proficient at reading lips. If you give it like a movie with no sound, but people's lips are moving, it can identify what they're saying with a 97% accuracy. Humans, on the other hand, are 67% proficient. Now, machine learning models have also come this far that they can actually colorize black and white images with a pretty high accuracy. Machine learning models have also been built to add environmental sounds, speech, and other sounds. So just imagine, now it's actually possible, although it's mind-boggling, that you can take black and white movies with no sound in them and actually make them colored movies with all the sound, all the dialogue. I think it's pretty crazy. So that's cool, but what has actually led to all this? So there has been a 300,000 times increase in the AI compute used from 2012 to 2019. It's not produced, it's used. So what has led to that? So the advancements in graphic cards. So I don't know how many of you guys know, but CPUs can go up to tens of threads. Graphic cards can go up to thousands of threads, and which is really beneficial for machine learning. Also, advancements in cloud technologies make it much accessible, much more experiments. You don't have to buy like rigs and rigs of all these machines, do some experiments, and what do you do with that, right? So now it's so easy and so accessible. Also, there are a lot of open source libraries like TensorFlow, for example. So let's talk a little bit about some historical developments in data and machine learning. Computers learn to identify cats. So what's the big deal, right? So we've been historically teaching computers to identify objects like this is pictures of cats, dogs, humans, males, females, cars, all that. But in 2012, some scientists researchers at Stanford and Google were able to create unsupervised machine learning models, which what that means is you just define the attributes of cats, not showing it pictures of cats, but by just defining them using programming. And it was able to identify cats, which was a great leap in machine learning. It's really important because it takes a lot of time to take pictures, label them, feed them, and then do all that training. So this was a giant leap. Also, on the same note, machines can see better than humans. So what does that mean? So there's been an ImageNet contest that's been going on. The main goal was to create machine learning models to identify images and catalog them in a certain category. So it was launched in 2010. By 2015, the accuracy of it increased from 71.8% to 97.3%. The best human whose full-time job is to catalog images, his accuracy is 94.9%. So this also promoted researchers to make models which could identify data more accurately. Search engine Baidu actually took it one step further. They took the model and actually trained it by taking the same images and skewing them, changing the colors, cropping them, cutting them out in different shapes. So they actually took it really, really further. So you might, so a lot of you might have heard of Gary Kasparov. He was beat by a computer called Deep Blue in '97. So here's this guy, his name is Lisa Dold. He is a winner and 18-time world title champion of a game called Go. So this game is hundreds of year old game from China and has been one of the biggest challenge for AI enthusiasts to crack because of its complexity. At any time, there are 100,000 moves for you to make in Go versus 400 in chess. So in chess, you could take some algorithms like decision tree and brute force and figure out what are all the different combinations, what can happen down the lane. But with this, it's almost impossible. So what happened? This machine actually beat the best player of Go of the past decade, 4-1, and is currently the best player of Go in the world, which I think is pretty funny. So this was a huge milestone from machine learning. So this game actually did some things that were pretty interesting. It actually, in game 3, it actually took some moves which people thought would be detrimental for you to win the game, but he actually played this move and actually was really, really helpful to actually win the game. So people are actually studying the game 3 specifically and all the other moves the computer made. So how did we build this computer? So what was interesting was when they built this computer, it was never told what the rules of the game are. It was actually fed 100,000 games of online Go played by amateurs. So all it was fed was screenshots of the screens at any point in time. And over time, it identified the rules of the game and how to play the game. And then they made it play 30 million games of Go against itself. And over time, it just kept on learning and it actually beat the best player in the world. They had no idea what moves it was going to make at that time. All right, so talking of data, the economist in 2017 said the most valuable resource is not oil, but data. So think for a second, what makes a machine learning model? It's data, right? So if you have a ton of data, if you're Google, if you're Amazon, if you're Facebook, you have a ton of data on your users or your customers. Now building a machine learning model on top of that, it's really, really competitive advantage. It's almost an intellectual property you want to save much more than your data. So talking of machine learning models, they're only as good as your code, your algorithm, amount and variety of data you feed it. So a programmer created an intelligent program to play Nintendo video games. It was doing pretty well when it was playing games like Mario. So what it did was it was able to look at the screen and identify how to increase the score by doing random things at first and over time learned how to play the games. So when they tried to use it to play Tetris, when the game was, so when the last block was about to drop and the program was about to lose the game, it actually figured the best way to actually win at Tetris is to hit pause. So think about that. So that's not what you wanted to do, but mathematically, it's impossible to keep on playing Tetris. So the program figured the best way to do is hit pause and not lose the game. All right, so we talked a lot about machine learning models, algorithms, and frameworks. What do they really mean? A model is a mathematical structural output of the training you're trying to give or the learning from the data. The machine learning algorithms are engines that derive the model and make sense of the data by processing it. And machine learning frameworks are libraries or tools that help you build the models easily without having to be a PhD in machine learning, without having to know the nitty-gritties of your algorithm. You just have some data, you know which machine algorithm you're using, and it makes it so easy for you. So let's talk a little bit about what are the different ways in which we can train our models. So there are three basic types of machine learning. And you might say there's like 4 or 5 or 6, but so most people agree there's like 3 basic types. So first one is supervised learning. A simple example is image recognition. You teach your program how to identify images of certain kinds. Second one is unsupervised learning, where your program can identify some data trends. Third one, and a little bit complicated to apply, is reinforcement learning. It's primarily used in robotics, self-learning cars, and things like that. So supervised and unsupervised are mostly used because they are slightly easier to use. And reinforcement learning takes a lot of work before you can actually start using it. So the first type is supervised learning. So in this case, you know the results, you know the input, you know the output. So you have some data, you tell the computer what this data is of, and it learns to identify similar data. So for example, you're trying to create a cat classifier. You show it pictures of cats and other animals, and the pictures of cats actually have labeled cat, and the pictures of other animals have like dog or whatever. So it learns how to identify cat. So in this case, in case of classification, what you're trying to do is get a binary answer, yes or no, true or false, cat or not a cat. What if you have a series of values you're trying to get? How do you train that with supervised learning? So that's where regression comes in. So think of regression. So let's say you are trying to move to a different state, and you're trying to see how much money would you make if you move to that state based on your experience, based on your skill set, age, a lot of all these factors, and maybe some of them don't matter. So it gives you with the supervised machine learning in the regression model, what you can do is feed it some historical data, and based on that, it makes some predictions. Next, second type is unsupervised learning. With unsupervised learning, you don't know the desired result set. They have yet to be defined. You really don't know what it's going to spit out, like what kind of information it's going to get. So basically, you're trying to extract valuable insight from some data, either distribution of data, correlation, and patterns. So there's many techniques. So I'll go over a couple of techniques. One is dimensionality reduction. So dimensionality reduction is used when you have a ton of noise in your data. You have a ton of attributes you're trying to get rid of, which actually don't really matter to the machine learning model. So think of a spam email, for example. You have a ton of words in the spam email. I'm sure like some of the words can be easily eliminated, like some common use words like the, hello, of, whatever. So how it helps is, first, it helps you reduce the amount of data you're going to process. It helps you with the storage. And now your processing is much faster since you are processing lesser number of attributes. And also it helps you fit your machine learning model to use some algorithm you previously could not because of the amount of attributes. So like I said, spam email, you could also use it to identify paint defects in cars. So think for a second, robots are painting cars in an assembly line. How do you define a defect? It's almost impossible, right? So over time, the computers take multiple images and train themselves of what a defect looks like. Another way of doing it is using clustering. So with clustering, you have some data, and you're trying to identify clusters based on similar attributes. So it's one of the examples I can think of is you could use it in marketing. You're trying to identify customers which have similar likes, similar tastes, so you can market to them and get better results rather than just having like a generic marketing campaign and try to apply it to all the customers. The third one is reinforcement learning. So with reinforcement learning, I think it's pretty cool, and it's one of my favorites because I know the most about it as well. So it helps you make autonomous decisions by using an agent, which is learning by interacting with another model, which is the environment. So it is doing trial and error, trying to do random things initially. And how it knows it's doing well or not is based on a feedback function. It actually has a reward function, which it tells it, hey, this was good, this was bad. So based on the points it gets, or the feedback it gets, it knows if the action it did was desired or not, and it learns from that. So think of a robot, for instance, or a video game playing program. So let's talk a little bit more about a model agent. So let's say you have a self-driving car. So you're not going to take it directly on the road, right? So first you want to train it in a virtual environment. So your agent is your car, and it improves its driving based on the feedback from the environment. So the goal of your car is to follow the speed limits, keep in the lane, drive safe, basically. After you're done training it, you're probably going to take it in a simulated environment or like a controlled environment. So now the car is in the environment. There are other cars driving on the road. It's receiving feedback from its sensors, like how fast are the cars going in front of me, on the side. Is this car going to turn in my lane? Is a turn approaching? Is the road going to curve? All that, and it's trying to do all these calculations and ready to take some action based on what changes, what state changes. So we talked about 3 different types of machine learning, but how do we actually create our models? So, so first thing you want to do is research and identify a problem, right? Like, what are you trying to create a machine learning model for, and what are the type of predictions you're trying to make? Once you do that, next you want to gather and prepare some data. So you can get data from various sources. For example, pictures, if you're trying to create an image identifier. If you're trying to get some unsupervised learning, you could get data from big data sources on your on-prem, or you could get some census data. There are some public data lakes out there. You can grab data from there. After you get the data, you want to clean up some noise from the data, so the machine learning models are good. So in case of supervised, you also need to label some data, like these pictures of these things, and so on. In case of reinforcement, you're trying to create a reward function and your environment and programming your agent. Next, you want to set up your training environment. So you code and configure your machine learning libraries, pick your algorithms you're going to use. You train your model by pointing to the data or the environment. And the machine learning algorithm starts finding patterns in the training data and maps the attributes to the targets. After you build your model, next step is to see how well it works, right? So in case of supervised, you want to keep maybe 20 to 30% of your images aside, which are still labeled, and then feed it to your model and see how well it does. And based on the accuracy, you know how, like, is it 60% accurate, 70% accurate, 80% accurate? And then you want to look at the industry standards and see how well other models are performing. So you kind of get like a idea of how your model is doing. In case of unsupervised, you want to see how close the clusters are in case of clustering, how close the customers are within the cluster. Do their attributes really match each other? And how close are the clusters of customers to other clusters? So you want to make sure like the clusters are grouped together, but they also have some separation between other clusters. So that's how you know you got a good data set. Best way to do it is to actually go out and try and see how customers react. And in case of reinforcement machine learning model, you're already getting some feedback and you know how the model is performing and evaluate as you're evaluating it in the virtual environment. So there's a few things that can go wrong when you build your model. First one is your model works really, really well. Well, why is that a problem? It works really well. Well, the problem here is that when you train your model, you probably use very specific data set, which was of a certain kind, and you don't have a lot of variety of data. And now it's working really well for that kind of data. But once you introduce new data, you're going to see it's not going to work. So take an example of a wolf. So they try to create a model of husky wolf identifier versus, wolf identifier versus a husky dog. So the dog is on the right, the wolf is on the left. When they trained the model, it was working pretty well with a high accuracy rate. But when they introduced additional data, they saw that the model does not work that well. So what happened in this case was they took pictures of wolves against snow and pictures of dog against grass. So the model, instead of focusing on the facial features of the animals, actually started focusing on the environment, snow versus grass, as it was much easier for it as well. Other thing that might happen is your model really sucks. It's really, really bad. It's because it has not learned enough. You did not supply it enough variety of data again, not enough amount of data. So in this case, you have an apple classifier. It has a 40% accuracy. It's saying this is an apple when this is nowhere near an apple, yellow in color, the shape doesn't match. Similar models have 70 to 80% accuracy if you were wondering how accurate the model should be in this case. All right, so after you figured out you have all these issues with your model, how do you fix those issues? The first thing you want to do is data. Your model's only as good as your data. You want to increase the amount of and variety of data for your training. Another thing you could do is look at research your models and see if there's a better algorithm, a better way, a newer version of the machine learning algorithm library you're trying to use. Another cool thing I found out was you can create heat maps. Heat maps are visual representation using colors to identify where your machine learning model is focusing on. So you can visually see what it's focusing on, and it can help you identify some issues with the model. Maybe it's not doing what you're trying to make it do. So in this case, you have an identifier, a sheep identifier. As you can see on the image on the right, it's focusing on the white sheep. Is that a good model or bad model? It depends, right? If you're trying to identify the brown sheep, then it's a bad model. If you're trying to identify both sheep, it's a bad model. If you're trying to identify white sheep, it's a good model. So again, it depends, right? All right, so let's dig deeper into reinforcement machine learning. Like I mentioned, it's one of the least type of machine learning type used because of its complexity. You need to set up a virtual environment. You need to set up an automated feedback system. You need to set up a reward system, and you need to set up your agent model. And you also need a deeper understanding of the algorithms. That sounds pretty complicated, right? But don't worry about it. Like, I have a simple way of showing you how to use it. So let's go back to our self-driving car. So in case of car, what are actions? It can steer, it can brake, it can control its speed, basically. At any point in time, all the combination of these three things is an action. It's not doing one thing at a time. When you're driving a car, you're not doing one thing, you're doing a combination of these things. So at any point, the combination of these things is called an action. And then you can do some, you can define the min-max for safety, max steering, braking thresholds, and so on. Like I briefly mentioned, a reward function. What's a reward function? So the reward function is basically driving the behavior of your model agent. It can promote good behavior, and it also tries to demote bad behavior. So the goal is you're trying to promote ideal behavior from your model. So at any state, agent picks an action. Let me try to steer this way at this much speed in case of a self-driving car and get some feedback. Let's say points. Let's say you get 10 points. I tried this, I get 20 points. I tried this, I get -5 points. So based on all that, it's trying to figure out what is an ideal behavior, and it's trying to maximize the amount of points. So let's talk about states and episodes. So state is defined as current situation of an agent. Where is it in the environment and what action it took? So that's what the state is. Like, where is it currently? So let's say your goal is to go from point A to point B with your self-driving car. So your episode is basically defined as going from point A to point B. And all these individual states make up your episode. You might actually fail to reach point B, but that's fine. As soon as your last state approaches, that's the end of your episode. So we have a starting point and ending point, and all these states, action, rewards build up an episode. And then we add up all the rewards and evaluate how our model did in that episode. All right, so there's a concept of exploitation versus exploration. So in case of exploitation, your model learns what's a good behavior. Let's say the car is trying to keep in the center lane, is trying not to go too fast. It just works. But is that what you want? Do you want your car going at 20 miles an hour at a 70 mile an hour speed limit interstate? Probably not. So that's when you introduce the concept of exploration. With exploration, what your model is doing is adding some randomness. It's trying to do some random things which it hasn't learned yet and see what's the feedback I'm getting. So you can tweak your algorithm to explore more initially, later. So there's a lot of settings you could do. So basically you're trying to promote random behavior so it can learn more things. You don't want it to just like not learn new stuff because it's too afraid of trying new things. Other concept is called the discount factor. So how does that work? So let's say your goal was to go from point A to point B. The car needs to go from point A to point B. And the car only can go halfway. And it figures, okay, I got like X number of points. I'm pretty good. I'm done. Not really. So what you want to do is now you want to promote the car to keep on seeking more rewards. How you do that is by adding a discount factor. With the discount factor, any rewards which you get in the future are worth much more than the rewards in the previous state based on similar actions. So now the model is trying to do more things and trying to complete the whole episode. So as a result, your model will be slightly well balanced and work toward optimizing the rewards. All right, so that all is cool. We learned about reinforcement machine learning. We know how these concepts work, but how do we do it? I was in the same boat as you guys, or maybe not some of you guys. Some of you guys are experts here, but especially for the guys who are new to this, I was like, man, I learned about all these machine learning algorithms. I read a lot of articles, watched a lot of videos, but how do I do this? It seems so complicated, right? It seems humanly impossible for me to do this with my limited time and all that. That's when I actually came across AWS Deep Racer. So AWS Deep Racer is one of the fastest ways to get started with reinforcement machine learning. So I saw like somebody, which at that point I thought was a remote controlled car, and they're running it on a track. I'm like, what's the big deal? But once I found out you could actually train it in a virtual environment, I'm like, that's cool. And then put it on the track and it drives by itself. I'm like, wow. I'm like, it's really going to suck when it drives on the track. And what I saw boggled my mind. Like, it's like, no, it works. That was pretty crazy. And that got me interested in Deep Racer. If you want to get started, I'm sure a lot of you have AWS accounts. If you don't, you probably want to sign up. And I'll pause for a few seconds if you want to take screenshots. These are a couple of URLs I have. They can help you get started. So they give you around 8 to 10 hours of free Deep Racer training. So you can build your model, train it. After that, it's around $3 to $4 an hour to train it. So at least you get 8 hours of free training. All right, so I'm gonna move on to the next screen now. So talking a little bit about the underlying technologies, it uses AWS Lambda, CloudFormation, RoboMaker, and one of the major things it uses is SageMaker. SageMaker is a machine learning platform for AWS. For you guys who don't know, it helps you do on-demand machine learning. They have a lot of pre-built models you can get from the marketplace, and you can do your unsupervised, supervised. There's a lot of stuff you can do, and it also has a fully managed Jupyter notebook for you to experiment with. Next thing you're going to do is use some Python. If you're new to Python, don't worry about it. It's going to be pretty basic Python. If you don't know Python, that's fine too. It has predefined Python models or reward functions. Next, it's going to interact with the Deep Racer system, which is an integrated system. It helps you tweak your algorithm settings if you want to. It helps you create a reward function. It has a simulator where you can see how your model's working. So like I mentioned, you have an agent, you have an environment, it's interacting with the environment, and it's based off a PPO algorithm. So it does two things. It has two models. So first model, what it's trying to do is what action to take. And the other model, which is the value model, is trying to figure out what is the value of the action I'm going to take. Initially, it's just going to try to take random actions, right? It's going to say, okay, let me try to just move left with a speed of 2 meters per second, let's say. and see how that works, and so on. It's predicting this is the value of my action. And over time, it actually gets feedback and it learns this is the value, this is the actual value, and keeps on updating those values in its neural network. All right, so like I mentioned, it uses a PPO algorithm. It figures out some random actions and goes from there. Next, you want to create a model. They recently introduced these new types. So the basic type is time trial, where you're just trying to complete your track in the shortest amount of time. Another ones they have is object avoidance, where you have static objects on the track and your car is trying to avoid those objects. And the third one, which I think is pretty cool, is head-to-head racing. So there's another car and you're driving your car and it has a 360 view using a LiDAR sensor. Next thing you want to do is they have around 10 tracks. They keep on changing it. So you pick your track you want to train your model on. And the more tracks you train your model on, the better it's going to be. Remember overfitting? So you want to train it in more tracks. Next, you have some input parameters to give you the state at any time. So you have a track, it has a center line, and it has solid lines as the boundary. As soon as the car goes out, it gets reset and starts from the beginning. All right, so let's talk about a few parameters. Speed, for instance. What is your steering angle? What is the width of the track? In the existing track, it's the same, but I think it can change over time. AWS might add some more variable tracks. Distance from the center. Are all the wheels on the track? Okay, so next thing you want to do is set up your model actions. What is the maximum steering angle? And the granularity is what are the different variations? So let's say I set my steering angle to 10 degrees max and with 3 variations. Now it's actually trying to, so it can do +10, -10, and 0 degrees. So with max speed, I set 2 meters per second and granularity of 2. So it's going to pick 1 meter per second and 2 meters per second. Now, what are the actions? It's a combination of all the things we decided earlier. So three variations in the angle and 2 variations in the speed, 3 multiplied by 2, 6 actions. Pretty simple. Next, you want to pick some sample code or you want to build your own code. So once you go to the next step, AWS actually has some predefined samples, following the center line, staying within the 2 drivers, or preventing zigzag like a drunk driver. What I did was I actually took all 3 and divided the reward by 3 and the penalty by 3, because these are pretty good models, reward functions. This is what the code kind of looks like. You don't have to build it. I'm just showing you how it kind of works. First, you do create your reward function. It's accepting some parameters. In this case, I'm reading a couple of parameters, distance from the center and track width, into some variables. Next, I'm actually creating my reward function. I'm saying if you're near the center, I'm going to give you 2 points, and if you're further away from the center, I'm going to give you 0.2 points. And this is how it kind of looks like visually, if you're wondering. If you stay near the center lane, 2 points, outside 0.2, and if you go out, reset, no points. Now you want to train a model, so you define how many minutes you want to train a model for. I think it goes up to 8 to 10 hours, or you could do a few minutes. I would recommend doing at least 30 minutes. So this is how the model looks like when you're training it. It actually shows you what it's doing. As you can see, this model, hopefully the video works fine for you guys. As you can see, this model is pretty mature, but initially it was trying these random things. Why? Because it wants to exploit, right? So it wants to explore new things. All right, so how does the heat map looks like? So this is kind of showing you when the car is near the left side of the lane, it's trying to focus on the left border, and when it's near the right side of the lane, it's trying to focus on the right border. It doesn't want to go out. And you also get real-time feedback by looking at, at the bottom you have episodes, and on the left you have all these rewards. So based on the rewards, you typically want it to slide up, and if it's going down, if it's kind of staying stable, you probably want to tweak your model. It's not working that well. All right, so after it's done, you can race against others. Typically, I mentioned going to summits, physically race it. Unfortunately, it's not possible. So you can also take part in worldwide virtual races. Once your model is ready, you can actually pick a lot of virtual races. And a lot of time they have like cool prizes like getting Amazon rewards for your cloud account. You even get a chance to actually go to reInvent, which you probably don't want at this point, right? I don't want to go to reInvent this year. Anyway, so this is a 1/18th of scale 4-wheel drive car. It has a camera, USB, it has Ubuntu, it has ROS Kinetic. This is software, Intel Vino toolkit. And so it has a ton of sensors. It has a ton of software which drives it. They also have this new hardware called Evo, which comes with stereo camera for left and right and LiDAR for 360-degree view when you're driving against other cars. They also have an option of creating a deeper neural network. The default one is a 3-layer. The new one is a 5-layer. It's going to be slower learning, but it's going to learn deeper. So let me show you an example of how it looks like on the track. So this is one of the top 5 models in the world at that time. As you might see, it's kind of struggling. But a lot of people said they were expecting the model to just hug the center lane. So why is that not happening? It's because, and I'm just going to the next screen because I see a lot of people when they see the video, they're not paying attention to what I'm saying. So what's happening there is there's a lot of shadows. There's a lot of variance in the lighting. The friction is different. The real world is on the model environment. So it's trying to accommodate for all that. So that's why it doesn't work as expected. So if you want to get into more into machine learning, there's a lot of cloud technologies out there. Like I mentioned, AWS SageMaker. They also have a deep lens camera, which is a machine learning camera. They obviously have Deep Racer. They have SageMaker Studio, which is an integrated environment. Also for learning, my favorites are udemy.com and edx.org. They are really good resources. If you want to get some advanced skills, you want to get into some R, some Python, some SQL, get into machine learning libraries like TensorFlow, scikit-learn, PyTorch, algebra, calculus, statistics, and so on. I really appreciate you guys joining the session. Hopefully you got some fun out of it, some entertainment out of it, and some knowledge out of it. Thank you guys for coming. I really appreciate you guys attending this session.